In the video for the introduction to the fundamental theorem of calculus, I promised that for these definite integral problems, there was a short way of doing it that's based on the idea that the integral, well, the area problem that is represented by the integral has something to do with the antiderivative. And so, so this is it. This is sometimes called the fundamental theorem of calculus. It is the idea that if we have a definite integral to do, now this is only if we have an integral that represents an area problem, so it has numbers here, then the answer to this is going to be capital F of 5 minus capital F of 1. So the 5 and the 1 here are entering into the answer, but I need to tell you what capital F is. Capital F is an antiderivative of the function inside the integration. We call that the integrand. So this guy. So an antiderivative of 2x plus 5. So that gives us a workable strategy for answering definite integral questions as long as the function that we're integrating is something that we can actually find an antiderivative for. So for example, in this case, an antiderivative of 2x plus 5 would just be x squared plus 5x. So this is an antiderivative question like we were answering before in section 13.1. It's checkable in the sense that I can just take the derivative of what I think the answer is. So I think the answer is x squared plus 5x. If I take the derivative of that, I get 2x plus 5, which is the integrand. So whenever I have an antiderivative answer, it's easy enough to check. So this will work as an antiderivative of 2x plus 5. And so the fundamental theorem of calculus tells me that the answer that goes here is just capital F of 5 minus capital F of 1. And each of those numbers is easy enough to find. Capital F of 5 is 5 squared plus 5 times 5. So if you do that on your calculator, you get 50. I'm using this expression. Capital F of 1 is 1 squared plus 5, which is 6. So the answer here is 50 minus 6, which is 44. Now let me just say a quick word about notation that they use in the book and that's used pretty commonly in calculus. A lot of times, to save time, people don't stop and actually write capital F equals something and then plug numbers into it. They tend to do this more on the fly without introducing the extra notation. So for example, you might see this solution in the book or online where I have the integral of 2x plus 5 from 1 to 5. You might see someone just write down an antiderivative of the integrand and then put a vertical line and write x equals 1 to x equals 5. And what they mean by that is to do that subtraction problem, to put 5 in for x, which would be 50, and put 1 in for x, which would give you 6, and subtract. So it's the same thing, but this second method doesn't take as much time to write because we're not introducing this extra capital F of x function and then plugging stuff into it. We're sort of doing it on the fly. I'll prefer the capital F of x version, but I wanted to point the other out to you in case you came across that in a solution to a problem. You would know that that's really the same thing, just shorthand. So our ability to do definite integrals then is only limited by our ability to do antiderivatives. In this case, I can find an antiderivative of 6 over x. It would just be 6 times the log of x. Again, that's log of the absolute value of x. You'll notice that when I'm using the finding an antiderivative here, I'm not putting the plus c down because the fundamental theorem of calculus says I can work with any antiderivative of 6 over x. I don't have to work with something that describes all the antiderivatives. So it doesn't matter which one you use. Anything that has a derivative of 6 over x will work. So to illustrate that, I wouldn't do this normally because it's not necessary, but just to illustrate the point, I'll put 6 log x plus 7. That does have the right derivative. If I take the derivative of capital F, I do get 6 over x, the integrand. So I know that that is a correct antiderivative. And so the answer to the question is just capital F at 10 minus capital F at 5. And if I do capital F of 10, that's, 6 log of 10 plus 7. And capital F of 5 is 6 log of 5 plus 7. Now, be careful with the parentheses here. Leave the parentheses on and just evaluate inside the parentheses. Don't just drop parentheses off or you'll get a different answer. So going to the calculator, 6 log of 10 plus 7 is 20.8155, etc. And 6 log of 5 plus 7 is 16.6566, etc. So I could just do that subtraction and get a number. Now notice that if I do that, that number is only going to be as accurate as I have decided to copy the numbers out of my calculator. So if you don't copy very many digits out of the calculator, then it's not very accurate. And even if you copy all of them that are on your calculator, it's not a perfect answer. So in a lot of these answers, it'll ask you to write the exact correct answer. And to get the exact correct answer, I would just take this guy and just simplify it as much as I can. I have 6 log of 10 plus 7 minus 6 log of 5 plus 7. So this plus 7 is going to be minus for that 7. And so I end up with 6 log 10 minus 6 log 5. And if you're feeling super ambitious with the algebra, you can simplify that a bit more. And if you're feeling really ambitious, you can use a log rule to simplify that even further. But I'm pretty sure that as far as course compass goes, this version is perfectly fine as the final answer. But that would be the exact correct answer. Here we have another example where the big issue is going to be to find an antiderivative. Don't forget that in section 13.1 it was not crazy that we might have to rewrite a problem because we really don't know what to do unless we have x to a power or e to the x. Those are the only things that we can find antiderivatives for. So instead of the 8th root of x here, I would want to write that as x to the 1/8 power. So my antiderivative rules say that I should leave the 8 alone. I should have x to a higher power, higher by 1, so I've got to add 1 to 1/8. 1 plus 1/8 is 9/8. So you do that over here on the side. We rewrite 1 as 8/8 and do that. And then in front of the expression here, I need to have the reciprocal of 9/8, so that would be 8/9. So this is 64/9 x to the 9/8. And again, I don't have to just assume that's right. I can check. I can take the derivative of that answer. And if you do that, you'll see that that really is 8x to the 1/8 power. So that will be right, and I can do that by just checking the derivative. So again, it's asking me for the exact answer. So I'm not going to do a numerical calculation here. I'm just going to find f of 1 and f of 0 and subtract. Fortunately, those are numbers that work very nicely with this expression. F of 1 is just 64/9, and f of 0 is actually just 0. So when I subtract the two, I get 64/9 as an answer.